In this video, we'll talk about the polar decomposition of an n by n matrix. And we can think of this as an application of the singular value decomposition. It's another matrix factorization. Well, the singular value decomposition is for any n by n matrix. But suppose that we have a square matrix. So the theorem says that any n by n matrix A has the form A equals P times Q, where P is an n by n positive semi-definite matrix and let's, in case you don't know what positive semi-definite matrix means, it means that it's a symmetric matrix and its eigenvalues are non-negative. That's what positive semi-definite means. So P is some positive semi-definite matrix and Q is an n by n orthogonal matrix. And the proof of this actually follows quickly from the singular value decomposition. So the proof is, take a singular value decomposition A, which is U times sigma times V transpose. Well, we can write A as U times sigma times U transpose times U times V transpose. Because U is an orthogonal matrix, U transpose times U, this is the identity matrix. So I'm just inserting an identity matrix in there, but notice that I have this factorization like this. So let P be U times sigma times U transpose, and Q be U V transpose. Now notice that U V transpose is defined. In general, for an n by n matrix, it's not, because U is n by m, and V is n by n, and you can't multiply n by m by n by n matrix if m is not equal to n. But in this case, A is a square matrix, right? So m is equal to n, and so Q is actually defined. And this is a product of orthogonal matrices. If U is orthogonal and V is orthogonal, then V transpose is orthogonal, because the transpose of an orthogonal matrix is orthogonal. It's just the inverse of the orthogonal matrix that's orthogonal. And so the product, U times V transpose, is orthogonal, because the product of orthogonal matrices is orthogonal. So Q is orthogonal. Okay, so Q is fine. Now how do we know that P is positive semi-definite? The reason is because when you have a matrix that's decomposed like U times sigma times U transpose, this P is U times sigma times U inverse, because U transpose is U inverse, because U is orthogonal. Okay, and when you have a matrix that's written like this, where this is sigma is a diagonal matrix, right? There's no, you're not sort of filling in things with extra zeros. Now, this diagonal matrix may have zeros on the diagonal, but you have, like, this is a square matrix, is what I'm trying to say. This is an actual diagonal matrix, and when you have a diagonal matrix like this, it's not kind of sort of like an n by n, it's like somehow a not square matrix, but it's somehow diagonal. I mean, this is actually a diagonal matrix, an n by n diagonal matrix. When you have a decomposition like this, the eigenvalues of P are just the diagonal entries of sigma. And we know that the diagonal entries of sigma, those are the singular values. We know that these are greater than or equal to 0. So P has non-negative eigenvalues. Now how do we know that this matrix is symmetric? Well, let's take the transpose. If you take the transpose, we want to show that you get P. And if you take U sigma U transpose and take the transpose of that, then this is going to be U transpose transpose times sigma transpose times U transpose, right? Because if I have A times B times C transpose, that's going to be C transpose, B transpose, A transpose. So I get this, and U transpose transpose is just U. Sigma transpose, what's sigma transpose? It's sigma, because sigma is a diagonal matrix. And U transpose is just U transpose, and I get U sigma U transpose, and that's equal to P. And so P transpose is equal to P, so P is symmetric. And since P is a symmetric matrix, and its eigenvalues are non-negative, we conclude that P is positive semi-definite. So P is positive semi-definite. This is U sigma U transpose. Q is orthogonal. A is equal to P times Q. So Q is orthogonal. That's what we've shown. And A equals P times Q. And that's the proof. And this is analogous, this A equals PQ decomposition is analogous to what you have when you have a complex number, because any complex number has the form R e to the I theta. And this e to the I theta, what you do when you take a complex number and multiply it by e to the I theta, it rotates by theta degrees. Well, I guess if theta is in radians, then it's theta radians counterclockwise. And then, of course, if you multiply, so R is a real number here, right? R is a real number. And of course, when you take a complex number and multiply by a real number, it stretches that number by a factor of R. So you can think of Z as doing two things. First, you rotate, and then you stretch by a factor of R. And when you have A equals P times Q, if Q is, so we have to be careful about what exactly it means to rotate a vector in Rn, right? I mean, Q is an orthogonal matrix, and some people are a bit sloppy and say it's a rotation, but you know, if Q is a 2 by 2 orthogonal matrix, it could be a reflection. It doesn't have to be a rotation. You don't think of reflecting as rotating. At least I don't think of reflecting as rotating. Rotations for me are matrices with determinant 1, and Q might not have determinant 1. So, okay, and P is positive semi-definite, but if you think of Q as like sort of like rotation, and P is positive semi-definite, so that means that, okay, it's diagonalizable. It has this matrix decomposition U sigma U inverse. And so what P is doing is it's not stretching the axes E1 through En necessarily, but it is stretching certain axes, if I have the matrix U, which is U1 to UN, then what P is doing is it's stretching the UIs, these vectors, these are orthogonal, by the sigma i's, right? And these eigenvalues are non-negative, and so it's stretching the UIs. These UIs are eigenvectors, and P is stretching them by a non-negative factor. Okay, so this A equals BQ decomposition is analogous, it's not exactly the same, but it's analogous to expressing Z in this polar form. This is the polar form of a complex number. So that explains the name polar decomposition. And so apparently, according to the book that I'm reading, this decomposition is used in mechanical engineering. Okay, I don't know anything about mechanical engineering. Okay. So it's used to model the deformation of a material. The matrix P describes the stretching or compression of the material in the directions of the eigenvectors of P, which are the U1 through UN. So yeah, exactly. The UI directions are being stretched by a factor of sigma I, and Q describes the rotation of the material in space. Okay, so if Q, say, has positive determinant, then, okay, again, it's not clear what exactly a rotation in, Rn is, but at least in R2 and R3, which is probably what they're referring to, an orthogonal matrix with determinant 1 really is a rotation. You are rotating in R3, you're rotating by an axis. In R2, you're rotating the whole plane. So, yeah, if you have R2 and R3, which I'm sure is what they're referring to because we're talking about, real life, then orthogonal matrix with positive determinant is going to be a rotation. That's a theorem about orthogonal matrices. But in general, for this PQ decomposition, Q might not have determinant 1. So it's not necessarily a rotation matrix. Okay. That's the polar decomposition. I just wanted to make this video just to explain that it's an application of the singular value decomposition, just to give an application. Okay, thanks for watching.